Hello, everybody. We are continuing today on section 3.2, which is polynomials. And tomorrow is your test. That's priority number 1 on sections 2.5, 2.6, and 2.7. But after today's video, you will be totally equipped to do the homework that's been on MyMathLab for a few days. So please carve out some time to finish that homework too. But priority number 1, make sure you are prepared for that test tomorrow. Okay, what have we talked about polynomials so far? Well, they have a smooth curve. Their domains are always all real. They never have a sharp, jagged turn. The leading coefficient and the degree tells you how it ends, going from left into right. If the leading coefficient is positive, it rises to the right. And if the degree is even, then both sides will behave the same way. And if the degree is odd, then there will be a change. It'll rise one way and fall the other way. Well, this function g, we're going to talk about all those things again, but this function g is just taking it one step further back and having us do a little bit more work before we find all these answers. First of all, I know a lot already. The degree is 4. It's an even degree. So that means the end behavior is going to be the same, left and right. The leading coefficient is positive 3. And since the end behavior is the same left and right, and the leading coefficient is positive, I know it's going up to the left and up to the right. I can figure out the y-intercept very quickly just by plugging in 0. So I can find a lot of information. But the zeros are hidden, and that's an important thing to find. So this section and the next one, we'll talk about how to find these zeros. For now, the tool that we use will be factoring. Not everything is factorable, but this one is. And when you're factoring, what you always look for first, it is without question the GCF. The GCF always makes your life a lot easier. And these 4 terms all happen to have an x in common. So you would factor out that x. Now the other factor, 3x cubed plus x squared minus 27x minus 9, all these 4 terms, this is also factorable. And when you have 4 terms, you factor by grouping. And that means taking the GCF out of the first 2 and then taking the GCF out of the second 2. Well, the first 2 both have x squared in common. And if I take out an x squared, I'm left with 3x and I'm left with 1. And you connect that by multiplying. So x squared times 3x plus 1. These 2 have a negative 9 in common. When you factor that out, you're left with 3x plus 1. Now, can you articulate the next step? The next step was just like the previous step. Remember the step we just did? You find the GCF and you take it out. That's what's going on here. But look at it as you got this group over here and this group right here. And those 2 groups have something in common. They both have 3x plus 1. So when just like when you factored out x squared plus 1, you ended up multiplying what was left over, 3x plus 1. You do the same thing here. We're going to factor out 3x plus 1 from these 2 green groups, and I'm going to multiply by what's left over. Well, what's left over from the first group is x squared, and from the second group is negative 9. So at this point, we're almost done, but there is a difference of squares, which you have to be, difference of squares are very, very popular. They happen all over. X squared minus 9 is going to be x minus 3x plus 3. All right, so now it's completely factored. One way I know that is because all the variables are raised to the first power. Can't reduce it further than that. So everything is to the first power, so it's totally factored. And the degree, I knew it was 4, so I know there were at most 4 unique zeros. And because of factoring, I know exactly what the zeros are. There are indeed 4 unique zeros. The number 0 is a 0. The number negative 1/3 is a 0, makes this factor 0. The number 3 is a 0, and the number negative 3 is a 0. And all those zeros are real. What does that mean? That means that all those zeros are x-intercepts. So if I were to graph this, it would hit the x-axis 4 unique times. Since the degree is even, we talked about this already, the end behavior is going to be the same on left and right. And with the positive coefficient being, with the leading coefficient being positive, it rises to the right, rises to the left. The y-intercept always occurs when x is 0. So just by replacing x with 0, we discover that the y-intercept is also 0. By replacing all the x's with their opposites, we will determine if it is odd or even, or maybe neither one of those things. Well, replacing all the x's with their opposites, the opposite of x to the fourth power, all those negatives cancel out, so it just becomes 3x to the fourth. The opposite of x to the third power, though, you have an odd amount of negatives, so one of those negatives remains, changing this plus to a minus, so it's minus x to the third. Here, the opposite of x squared, the negatives cancel out, so it's just negative 27 times positive 1x squared. And here, negative 9 times negative 1 times x is positive 9x. Now, this is the result of replacing x with its opposite, and it is not the same as the original, so it's not even. And if I were to factor out a negative, I wouldn't get the original, so it's not odd. So I get to say that G is not even, it's not odd. That means it's not symmetrical on the y-axis. That would be for even functions. And it's not symmetrical about the origin. That would be for odd functions. Finally, we could graph. So try to, from a distance, think about all of this information, really just the conclusions. We don't need to think about factoring, just the conclusions that we've got these 4 zeros that are x-intercepts. Well, here I graphed those 4 x-intercepts. So when I graph this, I know it's going to go through these 4 points. And I know it's a polynomial, so it's going to be curved, smooth features, and it's going to be continuous, so I'm never going to have to lift up my pencil. The end behavior helps. Since the end behavior is up to the left and up to the right, then I know that as soon as I pass this 0, it's going to be going up to the left. And when I start graphing through this 0 on the right, it's going to be going up to the right. That might be a little too vertical, but up to the right. The y-intercept is 0, so what I do is I just graph, knowing the polynomials look like they are smooth, continuous curves. I just have to graph, making sure that I hit all 4 of these zeros. So I kind of work backwards, and I pass through that 0, and this is a horrible job. I know I have to turn around and hit this, so I do a turning point, and I have to turn around again and hit this order pair, and then turn around one more time. Yikes. So that's a very rough, ugly sketch of what this function would look like. But the key things are the end behavior is up on the left and the right. It's hitting the x-axis 4 unique times, and that would be full credit. Something about the multiplicity of zeros, though. The multiplicity of a 0 is how often does that 0 occur, that single particular 0 occur. That last example that we just finished, there were 4 zeros, and they each occurred once. So they each had a multiplicity of 1. But if this ended up being x minus 3 squared, then the 0, 3 would have a multiplicity of 2, because there were 2 factors of x minus 3. Well, when the multiplicity of a 0 is 1, how does that relate to the graph? That means that when you graph the function through that 0, through that x-intercept, it's going to pass right through as if it were something of a degree 1, as if it were a line. If there's a multiplicity of a real 0 of 2, or in fact any even integer, it's not going to pass through. It's going to be tangent at that point. So degree 2, think of polynomial or quadratics, a parabola. So if the multiplicity of a 0 is 2, then the graph is acting like a parabola at that point. So it's just tangent. It comes down to the x-intercept, touches it once, and then swoops up again. Or coming from the bottom, it rises up to the x-intercept, touches it for one value, and then turns down again. But that's true for all zeros with a multiplicity of an even, whether it occurs 2 times, 4 times, 6 times, whatever. If the multiplicity is an odd, it occurs an odd amount of times, 3 or greater, in fact, because remember, if the multiplicity is 1, it just passes through as if it were a line. But if it's any odd number above 1, then it still passes through. It still passes through, but it flattens out at that point. and that would be called an inflection point. So for example, here is a new function with it's in factored form, thank goodness. And since it's in factored form, I get to know the zeros. This first factor tells me that the number 0 is a 0, because if I replace x with 0, this will be negative 4 times 0, which will be 0, and that's being multiplied by everything else, so the whole thing would go to 0. Well, that 0 has a multiplicity of 2. It's being squared, so it occurs twice. That means that when I graph it, it's going to be tangent at that point. At the point x equals 0, the graph would look like a parabola. It would be tangent to it. Here, this 0 is negative 5, and it occurs 3 times, because I can expand this as x plus 5 times x plus 5 times x plus 5. So there are 3 negative 5s. Well, that's an odd number. And if the multiplicity is an odd number, 3 or greater, then it passes through, but it flattens out at that point. So when x is negative 5, the graph would pass through at negative 5, but as it approached negative 5, it would flatten out a little bit. It would be an inflection point is what they say. So I always think of it as if you're driving a car along the graph and it's curving you would be turning your steering wheel to the right a little bit, and as soon as you pass that point, you would turn the steering wheel left a little bit to stay on the path. So that little switch of turning your steering wheel would be the inflection point. And this 0 is positive 7/2. It only occurs once. So the graph just simply passes through as if it were a line at that point, a degree 1 polynomial. Let's see here. So let's graph this. See if I can do a better job. Now remember, the leading coefficient is a negative. If I were to multiply all this out, it would be, what would the leading coefficient be? It would be negative 8, because negative 4x squared times this would give me negative 4x to the 5th power, because I'd have to cube this first. And then when I multiply this, that negative 4x to the 5th power would be multiplied by 2x, making it negative 8x to the 6th power. So this is an even degree polynomial, which means the end behavior is the same left and right. And since the leading coefficient's negative, it's going down. And so I might just do myself a favor, and as soon as I pass this last 0, it's going to be going down, and same thing with the last 0 on the right. Okay, now I got to think this through. This 0 represents negative 5, this 0 represents 0, and this 0 represents 7/2, which is 3.5. So when I'm passing through negative 5 has a multiplicity of 3. So it's going to flatten out right there. It's an odd multiplicity, so it's going to pass through, but not pass through like a line, like this one does, but flatten out a little bit. Do my best to. We're going to accept that as an answer because this is too difficult to try to control it with the mouse. So I've passed through, but you see how I flattened out a little bit. And this is what I meant with the car analogy. Like if you're driving along this path, it's curving to the right. So you'd be tilting your steering wheel to the right until you reach this point. Then you start tilting your wheel to the left to stay on that path. And then my next 0 is the number 0, which has a multiplicity of 2. So it's going to be tangent right there. So since it's a polynomial, I do a smooth curve. And that was a mistake. I become tangent right there when x is 0. So notice it's touching that at exactly 1 point. Well, same thing here, but the key thing is it's not passing through. It's just tangent. And then my final 0 is 3.5, and that occurs just once, multiplicity of 1. So it just passes right on through as if it were a line. So I turn around and I just shoot right on through. So that's the best I can do with the tools I've got. Trying to draw it with the mouse is not easy. I'm sure you could do better with paper and pencil. One more slide very quickly. The thing is about turning points. this is you've seen this before in algebra 2 and in pre-calc, but polynomials, when you draw them, they have those smooth curves. And when you do a 180 along that path, if you're going up and then you turn around and suddenly you're going down, that's a turning point. And that has something to do with the degree. If there are 5 turning points, then the degree has to be at least 6. If there are 2 turning points, the degree has to be at least 3. So however many turning points there are, you add 1, and that's the least the degree could be. Think about a line. A line is a polynomial. Well, the line has 0 turning points. It never turns around. Well, that means the degree is at least 1, which of course lines are. Lines are a degree 1. Polynomials have only one. I'm sorry, quadratics only have 1 turning point. That means the degree has to be at least 2, which quadratics are. Quadratics have a degree of at least 2. So if the degree of the polynomial is n, then there are n minus 1 turning points. At most, n minus 1 turning points. So here, looking at this graph, we don't know what the polynomial is, but I can see 1, 2, 3 turning points. So this polynomial has to be at least a degree 4. It has to be at least a degree 4. It could be more because if I zoom out, it'll have more turning points, but it's at least 4. And then furthermore, since I know about multiplicities, I know about these zeros. First of all, the y-intercept is negative 4. Or is it negative 4? Based on the scale, I'm not sure, but the y-intercept is definitely negative. The x-axis here, I think this is supposed to be from negative 2 to positive 5, and the steps are going by 1. So this is negative 1, negative 2, 1, 2, 3, 4, 5. This would mean that the y is going down to negative 40 and up to positive 4, but the steps are by 4. So this y-intercept is negative 4, negative 8, negative 12, negative 16. So the y-intercept is negative 16. But this 0 is negative 1. And since it's tangent, that negative 1 occurs twice. So I could write this as a factor. That negative 1 is a 0 is acting twice, or any even amount. It could have been to the 4th power or the 6th power, but any even amount. But we'll just keep it simple, do the smallest even number. And there's one more 0 I can see, and that's when x is 4, and that is also tangent. So the value, the 0 negative, or the 0 positive 4 also occurs twice. So that would correspond to the factor x minus 4. Now, what have I got so far? I've got a polynomial that's a degree 4. And this one has 3 turning points, so it's at least a degree 4. So I could just have that be my final answer, except, remember, the leading coefficient, it's going down to the left and down to the right, so that my leading coefficient is negative. So this would be the beginning of trying to find this actual value. Now, to be totally correct, we'd have to do a little bit more investigating. I know, remember the y-intercept was 0, negative 16? Well, what would happen if I plug in 0 into this? Do I actually get negative 16? And I think you do. When you plug in 0 for x, this becomes 1 squared, which is 1. When you plug in 0 for x, this becomes negative 4 squared, which is positive 16. But then that positive 16 is being multiplied by negative 1, so you do get negative 16. This would be an acceptable answer for coming up with a polynomial for this. And the reason I say that is because this is a good practice for you if you like. In your textbook on page 379, you could actually go to your physical textbook, but going to My Math Lab and going on the e-text and typing into the box 379, this is a good exercise, 65 through 72. And what's cool about this is you could click on this little world icon and it'll give you an interactive. You know how when you do odds, you have to flip all the way to the back to see if you're right or wrong? Well, this one saves you the trouble. Here are all the odds in that section. So let's say number 65. You can just type in your answer into here and see if you're right or wrong. And the computer will check it for you. It will have no impact on your grade. It's just a way to check your answers. Mine's taking a second to load, but this is number 65 from your text on page 379. So you fill it in, and then it's a nice way to check.